So this stuff is everywhere and it's kind of weird, but you need it for life and you probably need to know about it for a test. And it really feels like it should not be this confusing. So let's clear that up. Hi, I'm Sarah and I'm your other biology professor. Let's talk about water. In this video, we're going to take a look at some common student misconceptions dealing with the structure of water molecules and how that structure impacts how water molecules interact with each other. If you're looking for tips on the properties of water, stick around to the end where, spoiler, we'll talk a little bit about ice. And we'll cover some more properties in another video. If you've reviewed your water structure, you'll remember the importance of partial charges. And with all the talk of charges, a lot of students get the idea that water molecules are charged, but that's not the case. If you take a look at a periodic table, you'll notice that hydrogen has an atomic number of 1. That means that our hydrogen atoms are going to have 1 proton and 1 electron each to make a neutral hydrogen atom. Oxygen atomic number is 8, so 8 protons and 8 electrons to make that neutral oxygen. So if we tally all that up, that's 10 protons, 10 electrons, and that's what we still see in the water molecule. We didn't lose anything, we didn't gain anything to make the water, so we didn't lose or gain any charge here. The other sort of more obvious hint that water is not a charged molecule, not an ion, is that we just write it as H2O, not H2O plus or H2O minus. None of that going on here. What we do have are asymmetric charges across the water molecule, right? We've got a positive pole, a positive end of the molecule over here where the hydrogens are, and we've got a negative pole on the oxygen end. So not only does water contain polar bonds, individual bonds where electrons are shared unequally, giving us partial charges, but the molecule itself has polarity, right? It's got ends that are partially positive and partially negative. So we can correct our misconception by saying, no, water's not charged, but it is polar. Common misconception number 2 is that hydrogen bonds hold a water molecule together. And if you recall your water structure knowledge, you'll remember polar covalent bonds are what hold the water molecule together. Okay, so where do the hydrogen bonds come in? Well, they don't until we get more water molecules. There we go. So this is the same thing, water. It's just that instead of little circles and dots, we're representing it now as a little bit more of a 3-dimensional shape, right? Which is what water actually has. So now I've got 2 water molecules over here. And this is where all of those partial charges we spent so much time looking at are going to come into play. The partial positive charge on one water molecule is going to be attracted to the partial negative on nearby water molecules. And that is a hydrogen bond. It's an intermolecular force, which means between molecules. So you got to have more than one. Whereas the covalent bonds are an inside the molecule force, an intramolecular force inside the molecule itself, making the molecule. So that hydrogen bond, it's an attractive force between the partial negative oxygen on one water molecule and a partial positive hydrogen on a nearby water molecule. No electrons being shared here. So calling it a bond is probably a really bad name, but that's what we do anyway. In liquid water, these are really, really transient, which means they're temporary. Water molecules are moving around constantly, so they are forming and breaking and reforming hydrogen bonds with new partners all the time. These bonds are much weaker than the covalent bonds that hold the molecule together. But they are still really important. I've got 3 pairs of molecules here. So in their current positions, so without moving anybody around, Which pair or pairs of water molecules are the most likely to form a hydrogen bond? Pause the video and think about it if you need to. Ready? All right, if you said this last pair, well done. Why? Well, I said in their current position, so you're not moving anybody around. The partial negative of the oxygen of one water molecule is already oriented towards that partial positive hydrogen on the other. So those are going to attract. Whereas our other pairs are oriented so that we've got partial negative facing partial negative and partial positive facing partial positive. Those are not going to attract each other. So you're not going to see any hydrogen bonds there. Okay, one last misconception for the day, and that is that water only forms hydrogen bonds when it's in its liquid state. So we just talked about how the hydrogen bonds in liquid water are very dynamic, right? Water molecules are very dynamic in their liquid state. They're moving around. As they get close to other water molecules, they'll form hydrogen bonds, but then they'll break, and then they'll form new bonds with other molecules as well. Well, if we start to lower the temperature of the water, the movement of the water molecules slows down, and the molecules will get a little bit closer together. Water becomes more dense. That is typical of what happens with molecules when you drop the temperature. That happens until about 4 degrees Celsius, so just above freezing. And that's when water starts to get a little bit weird. So at that point, the water is super cold, the molecules aren't moving very much, and they're very close together. That means it becomes very easy to form hydrogen bonds. You've got bonding partners right there all around you, and they're not moving enough to break hydrogen bonds. So at that point, you're actually going to see the number of hydrogen bonds go up. So water molecules are going to form more hydrogen bonds. Each one can form up to 4. And when that happens, that's going to actually increase the space between the water molecules, forming a crystal structure, getting more stable hydrogen bonds. That's why ice is less dense than liquid water. Look at all that empty space. Now, as we raise the temperature and ice starts to melt, some of those hydrogen bonds will break, and the molecules can get closer again, less dense. So in reality, all states of water form hydrogen bonds. Ice does it a lot. Lots of hydrogen bonding in ice. A good amount in water, constantly forming and reforming. And if you're wondering about steam, the molecules in steam are very far apart, so that doesn't give a lot of opportunities to hydrogen bond, but there is a little going on when molecules do happen to get close enough. Oh, and fun fact, the expansion of water when it freezes is one of the key properties of water. It means that ice floats. We're going to look more at properties of water in another video, and I'll give you some tips on how to not mix them up. One last little bit of practice before we go. I've got the 3 states of water very crudely sketched down here at the bottom. See if you can figure out which one is supposed to represent ice, which one is liquid water, and which one might be steam. Ready? If not, pause the video a little bit longer, but let's take a look, starting with steam. So the one where the molecules are the furthest apart from each other, and sort of randomly distributed, is going to most likely represent steam. Remember, very little, if any, hydrogen bonding going on because of that large distance between molecules. How about on the far right, where we've got a very ordered distribution, very even, regular distribution of our molecules? That one's our ice, with that regular crystal structure that develops as a result of having very stable hydrogen bonding, maxing out the number of bonding partners between each molecule. And so that leaves us the first one as liquid water. Randomly distributed molecules, because they're going to be moving all over the place. Able to get close together, but not in any sort of discernible pattern. You're going to see hydrogen bonding happening here, absolutely, but not to the extent that you'd see it with ice. This water looks nice and dense, so it could be very cold. All right, I hope our little tour of water was useful for you. If so, please give this video a like so that other students can find it as well. Be sure to check out my website for the latest and greatest of whatever I've got going on, some more biology, of course, and I will see you next time.